So, good evening, ladies and gentlemen. I'm Ronan Keane. I'm the Chair of Engineers Ireland Cork region, and I'd like to welcome you this evening to lecture on the design and construction of diaphragm walls. Our speakers this evening are David Hard, Chief Engineer, and Tim Casalis-De-Pury, Pre-Construction and New Business Manager with Bachy Soletanche. So, without further ado, I'll hand you over to Tim and David.
Thank you very much, Ronan. As per the introduction, my name's Tim. I've worked for Bachy Soletanche for a couple of years now in my role as pre-construction new business manager, so sort of business development, but also working with the estimating team and coming up for solutions for clients' problems. And prior to joining Bachy, I worked for another geotechnical piling and underpinning contractor here in the UK. A lot of retrofit basements underneath existing structures and underpinning houses as well. So my background is civil engineering. Dave, do you want to introduce yourself?
Yes, good evening. David Hard, as mentioned, I'm Chief Engineer for Bachy Soletanche, so looking after the sort of the technical and design side of the company in the UK. I joined the group back in the early 90s, quite a long time ago. I've worked around the world with them since then, but nearly always in the design office. When I started my career as a student on diaphragm walls, so this is something that's been sort of in the background of my entire career, even if we don't always use them as much in the UK as they do elsewhere on the continent.
Fantastic. So in today's presentation, I'm going to talk a bit briefly about our business and our business units in the UK and Ireland. And then we'll get into what the presentation is really about. What is a diaphragm wall and some of the techniques that we use to create them. And then Dave's going to take over, talk about the design and execution, some key quality and testing points. And then at the end, we'll have some questions and answers. So Bachy Soletanche, who Dave and I work for, is a UK registered company. And we undertake quite a lot of different geotechnical techniques. So I won't read all of these out, but a lot of what we do is piling within the UK. So large diameter rotary, CFA, cased secant piling, CSP, some people call that cased CFA, so CCFA. And we use those quite regularly for bearing piles and also retaining walls, either secant or contiguous. We've got a number of different techniques that we can sort of add on to those things. So under reams, plunge columns, we can thread various types of different pile as well. We've got small equipment, so we can do restricted access piling. And then we can also do marine-based, near shore primarily piling that we do as well. Subject of this talk is diaphragm walling and barrettes. If you're not familiar with that, a barrette is just a distinct section of a diaphragm wall on its own. So that would tend to be sort of a bearing section, but created using a diaphragm walling technique. I'm not going to talk specifically about it, but that's for your information there. We do a large number of grouting techniques, and also soil mixing tends to be deep soil mixing that we do, along with various techniques for securing retaining walls, so soil mailing and ground anchors. And finally on that list, cut-off walls, so to prevent progress of groundwater or contamination in the ground. We've got various different techniques we can use to stop that from happening, and also permeable and active barriers as well that we can install within the ground. Now, we are actually a group of companies. So within the UK and Ireland, we have a number of sister companies. So starting sort of top left there, McDonnell Piling and Foundations is our only sort of wholly based in Ireland business unit. They are based in Cork. What they do is a CFA piling, mini piling underpinning. They do ground anchors and saw nailing and ODEX piling as well. Any projects we've got in Ireland, or quite often when we look at them, there's elements of CFA and rotary, and so we might sort of work together in a sort of internal joint venture to deliver projects over in Ireland when necessary and suits the skills that we can bring to various things. Other business units who do operate in Ireland as well as being based in the UK are soil engineering. They're a site investigation, ground investigation contractor. Got one of the largest materials testing and soil testing laboratories in the UK. They're also capable of doing bulk grouting. They tend to do sort of infill grouting, so collapsed mines, things like that, various different specialist drilling techniques. Bottom left there is Vibro Menard. Vibro Menard is the sort of ground improvement part of our business. So vibro stone columns are pretty common, pretty well known about. But on top of that, they've got controlled modulus columns, which is kind of a vibro stone column, but instead of stone using concrete. And then a bimodulus column, which is actually both of them used together. It's a lot more technical than that, but I wouldn't be doing justice trying to sell it. So if that's something that's of interest, no spoil, ground improvement techniques like that, it's definitely worth having a chat with those guys. And they also do various different types of compaction and band drains as well. In the centre is a Sixth Sense, used to be called Soletanche. This is part of our business that undertakes monitoring and more recently has sort of moved into data management, surveys, satellite information and mapping, and actually creating digital platforms for managing that information to enable clients and end users to manage their assets. So really forward thinking and progressive part of our business. I'm really interested in having a chat with those guys. So do take a look at their website if you're interested in some of that. Bottom right is quite a different logo to most of ours. They've been allowed to keep their sort of identity since we bought them, and that's Roger Bullivant. So Roger Bullivant are a long-standing UK-based driven piling primarily contractor. Do a lot of work in the housing and smaller end of the commercial market. So they've got a precast factory in the Midlands that can produce over 1 million metres of precast pile every year. It's quite a phenomenal facility they've got there. Alongside that, they do mini piling, underpinning, and complete house foundation packages as well. So we do have quite a wide presence in terms of our offices. Our head office, Bachy Soletanche head office, is in Burscough, Lancashire, so relatively short hop over to the island of Ireland. And then we've got other offices spread throughout, and obviously in Cork we've got McDonald piling as well. Within the group, we've got over 50 different specialist bits of kit that we can call upon. We've got 2 fabrication plants as well. Specifically, that is Roger Bullivant's plant in the Midlands, where they actually manufacture their own piling rigs. And our Bachy Soletanche plant up at our head office in Burscough, where we fabricate a lot of tooling and equipment. We actually export quite a lot of augers and things like that. We just produced some large augers for a sister company in Canada. So yeah, fabricating and building things is key to our business, building locally. We've got over 1,000 employees within our group of companies, and we are a design and build contractor. So Dave and his team, not all 30 people report to Dave, but there is a substantial design portion of our business, and that's one of the key values that we bring to projects, actually, is to be able to look at them and assist with the design and development of projects. If you're not aware, we are part of a wider global group. Soletanche Bachy turns over about 1.6 billion euros a year, has over 10,000 employees, and does over 4,000 projects every year. So where we need to, we've got that global resource and that global expertise, and particularly when it comes to diaphragm walling techniques. We don't have a lot of diaphragm walling equipment in the UK or in Ireland, so we do need to call upon some of that global resource pool at the moment. Although things might change depending on how demand for diaphragm walling goes, hence doing presentations and trying to get people interested in it. As a business, we've got a number of accreditations, probably most the sort of things you would expect from a sort of business of our size. So the normal sort of ISO accreditations. We're also members of the European Federation of Foundation Contractors, and then the Association of Geotechnical and Geoenvironmental Specialists. So yeah, a number of relevant bodies that we're members of and big supporters of as well. So enough of me talking about our business, onto the topic today, which is diaphragm walling. So what is a diaphragm wall? In its simplest form, it's a continuous reinforced concrete wall, and it's constructed from the ground surface downwards. They are always rectangular panels, although sometimes we put 2 together to create a T, and they are always excavated using a support fluid. So these excavations are not going to stand open like a rotary bored pile or something like that. They are always created using a support fluid to hold the ground apart. So some of the sort of pros and cons on a very sort of high level of diaphragm walls, they are structurally more efficient for retaining than circular piles. If you think of a circular pile section and you reinforce that, you're going to end up with reinforcement inevitably in that sort of neutral axis of a retaining wall, where it's not really doing anything. With diaphragm walls, we can reinforce the front and the back of a cage differently, depending on how the design goes. And also we can vary the reinforcement vertically as well. So we can really target where we need to put the reinforcement in, and we can have a very efficient shape. So generally you'll find the overall thickness of a diaphragm wall will be less than that of a comparative, say, secant piled wall or something like that. Because of the way it's constructed and the size of the panels, we end up with fewer joints per meter run than board piled retaining walls. And that is obviously good for water retention and also an element of sort of stiffness as well. With the nature of the cages in terms of how we install them and them being rectangular and able to sort of twist or anything like that, we are able to install slab connections and they're sort of ideal for top-down construction. So you can excavate down, get to the bottom of a diaphragm wall panel and have a knockout section or something like that where you'd be able to connect on. And we've got some examples later on when we talk about reinforcing these panels that'll just demonstrate that for you. We can actually install water stops in the joints of diaphragm walls. Again, we'll show you that a bit later on, but using the CWS joint that we've sort of developed as part of our process, we actually put a physical water bar in between each of the panels. So even where we do get a day joint, a construction joint, we're able to put a water bar across it and prevent water moving through. On the negative side, possibly, it is more expensive and the equipment and certainly some of the space requirements can be quite substantial. Again, we're going to show you that through the course of the talk. I think you'll get a feel for what it is, how much sort of space is necessary for it. But the quality and the depth that can be achieved can be worth it for the right sort of project. In a little bit more detail, the illustration on the right-hand side there is actually from Thames Tideway project where we installed the diaphragm walls, and you can see we've got some sections of diaphragm wall used for a sort of retaining element there. This is projection out into the Thames, so they're part of the sort of permanent retaining river wall that we've created. And then we've got a deeper section there, which you can see is a large cylindrical shaft. And then you can sort of see the two sections there where the tunnel boring machine will pass through that shaft as well. So it can be used primarily for shafts and retaining walls. I'll show you those in a second. Generally, the wall thicknesses vary from 600 to 1.8 meters thick, and there are sort of set intervals for those for the tooling and equipment. We can excavate over 100 meters, depending on the method that we use. We'll talk about that a bit later. And broadly, the two ways of excavating diaphragm walls are either with the use of grabs, and those are either rope or hydraulic, or using hydromills. And then the panels themselves are excavated in varying widths. Sort of the narrowest would be 2.7 meters and up to 7.5. And again, we'll kind of show you that as we go through, but it depends on the technique and the geometry of the structure that we're building as well. They're reinforced panels, and most of the time we're using standard reinforcement for them, but where we've got tunnels passing through, we need a soft eye, we can use fiberglass as well. And I mentioned before, they're always constructed using a support fluid. Support fluid is a sort of key element to a successful diaphragm wall, so we'll show you what that looks like as well. What do they look like when they're finished and excavated out? A couple of examples here. So top left is the Isle of Grain. This is what's affectionately known as the peanut. If you followed us, saw the chat on LinkedIn about this presentation, people were getting excited about seeing photos of the peanut. Well, that's what it is. And it's a self-supporting excavation. We've put some sort of fin walls between the sections there, but that could well be propped if you wanted to. And all of that was actually temporary works to facilitate a rectangular tank being installed within that peanut shape, because the ground was just so poor there was no other way of excavating that tank to that depth. So an interesting and quite innovative technique there. Top right, is Tottenham Court Road. You can see multiple levels of propping. Dave will be at pains to point out that was not our design of the propping, but it gives a good feel for sort of the depth and the finish as well. You can see there, that is the diaphragm wall finish that's achievable. And you can also see almost hopefully some areas where reinforcement sort of continuation box outs are in the face of the wall. So they're going to expose those and fix the slab then afterwards. So, and then lastly, sort of, so we've done a self-supporting shaft or a peanut. We've done a propped wall on the right-hand side, and in the centre at the bottom is an anchored wall. So there we've left reservations within the reinforcing and the concrete, and we've we've drilled and created supporting anchors in that case through to hold that wall up, so anchored from behind. We don't have a lot of sort of case studies to go through in this presentation, but to give you a feel for some of the projects we've done, here's a list of a few of them. Thames Tideway Tunnel, the eastern section, we are still working on that project at the moment. All of the diaphragm walling is actually finished. But on that particular project, we are we are a 20% stake in the JV delivering the works. So we as a business are able to function as a main contractor on our own, as part of a joint venture, or as a subcontractor. And the second project there, the Harefield shaft, is a good example of where we're working as a subcontractor, creating a couple of shafts for them then to subsequently use a TBM for a gas pipeline diversion. Similarly to Thames Tideway, Lee Tunnel was sort of the section before that as part of the overall London sewer programme for Thames Water. So similarly, we were in a joint venture there as a main delivery partner for it, and some very deep shafts created there, up to sort of 100 metres. I don't think we're going to go through every single one of these, but the point is, you probably notice a trend there that they tend to be quite deep shafts, and a lot of them are for infrastructure projects. And within the UK, that tends to be the case. The reason that diaphragm walling gets called upon is the need for high degrees of quality or tolerances, deep excavations. Whereas on the continent, it's quite common to use diaphragm walling techniques for deep basements as well. But it doesn't quite work out that well in the UK, just because we do like rigs that spin around in circles. That's just how we've all got used to creating retaining walls, is that we drill holes in the ground. Whereas on the continent, they still like to dig out panels. So yeah, just a sort of different in the market really over here. Just to give you a feel for what a Thames Tideway looks like, these photos have aged a bit now, but they were taken sort of middle of last year. Again, you can see the finish on the panels there of the diaphragm wall shaft that we've created. We've designed all of the sort of shaft retaining structures and all the reinforcement that goes into them. Yeah, fantastic project, really proud to have been a part of that one. So. Okay, so that's a sort of brief overview of diaphragm walling. So now we're going to get into the techniques that we use to create them. As I mentioned earlier, there's kind of two primary techniques. There's the grab, and then there's the hydromill, or as we affectionately call them, hydrophrases. That's sort of our terminology for those machines. It's probably more commonly known as a hydromill in the industry. But just a quick comparison between the two choices, really. So a grab. I'll show you what one looks like, but generally it's quite a small space relatively, but it does need desanding equipment. It has a bit of a capability to get through hard ground. You can use sort of chiseling techniques, but it is noisy and creates some vibration. Verticality is good, better than piling, and again, it relies on the sort of skill of the operators and also the correct instrumentation to get that. And we can use grabs up to 75 meters deep and thicknesses up to 1.5 meters thick. The Hydrophrase is quite a bit bigger in terms of the space requirements and the bit of kit itself. But what it brings is really, it can get through that much harder ground. In fact, it quite likes hard ground. It works quite well going through it. And fantastic verticality control. And as I talked to you about the technique, you'll probably understand how and why that is. Depths achievable with the equipment we've got, we can get up to 125 meters deep, and slightly thicker panels possible with Hydrophrase as well, so up to 1.8 meters. So I'll go through those two techniques, or three maybe. So first off, the rope grab. This is a pretty simple machine. It has it's a crane-mounted grab, and the grab itself has a couple of jaws on it that point down, and you lower that into the hole, and through its own weight, it digs in a bit, and you pull one of the wires, and the jaws close, and then you lift it all up with the other wire, and you bring it out. Interestingly, it's actually the most skilled drivers that end up operating these, because it relies a lot more on their sense and their sort of experience of using the equipment. So we do get some very good results with what these machines are able to produce, but obviously it has its limitations. It's relying on its own weight. It's, you know, it's a big chunky piece of kit, but when it comes up against an obstacle, it might struggle. So interesting thing to note from this photograph is the slightly odd edge protection. You might be noticing these sort of slightly odd sort of up and down bars. The reason for that is in the position that they're in at the moment, that keeps the guys well away from the excavation, nicely safe. There are points, particularly on this fixing reinforcement, that we need to get a bit closer to the excavation. So those bars can sort of be bent down through 90 degrees closer to the tooling, and allow the guys to safely get a bit closer to do some steel fixing or connect cages together or whatever needs to be done. So that's sort of an innovation that we've developed, and obviously safety is really sort of key for us. So the big sister to the grab is the hydraulic grab. This bit of kit is now using hydraulic power to close the jaws, and that allows it to put that much more force into actually digging into the ground. They are actually, as you can probably tell, they're just a bit bigger and a bit heavier. So whilst they're still relying on their own weight, they've got more of it, and so they can get through much more of the ground. So these are an excellent, useful tool where we need to have a bit more grunt to get through things. So what is the actual technique for creating diaphragm walls? So this sort of sequence here of drawing sort of, well, I'll talk through it, and hopefully by the end of it, you'll get a feel for how it works. So first diagram there sort of on the left is kind of trying to show that there's a guide wall that's been installed. So we always need to have a guide wall. It's what sets the tooling up to dig into the ground nice and neatly, and allows us to repeatedly get down into the ground accurately as well. And then on the second bit, it's kind of difficult to tell, but sort of on the left-hand side of that illustration, there is a diaphragm wall panel that's been constructed already. So there's one diaphragm wall panel in the ground adjacent to the one that we're actually going to be constructing now. And so to start digging, we drop the grab into the ground, we dig it up, and as we're creating a hole, we're constantly filling it with support fluid. So there's always a fluid in there, and that is providing hydrostatic pressure onto the edges of the excavation and keeping that hole open. It's a rectangular excavation. It's not inherently particularly stable on its own, so we have that support fluid in there to push the ground out and provide some stability for it. So we dig down in one panel, and what we do is the tool goes down, takes a grab, brings it back up, rigs slews around, deposits it either onto the ground or directly into a moxie or something like that to take the spoil away, turns back around, back down, and you just keep doing that until you've excavated your first bite of the panel. So bite is how many times we go down the panel to create it. So this example is a 3-bite panel. So we do the first section, that's as you're sort of looking at it on the right, and then we'd move over to the left. Now here we're actually adjacent to a section we've already dug. So we're kind of working down actually using the water stop that we put in previously. And that helps us actually to guide down, make sure we dig everything out around that water stop. So we dig down there, and then once we've done that bite, we've then got that third central section to do. And the reason that we do the middle bit last is that because you're digging under gravity on your two sides of your grab bucket, you can't have one side in the ground and one side, not in the ground. It would just sort of tend to lean over. So you have to have the sides balanced. So we leave that section in the middle, and just get on top of that nicely, give a bite into it and bring some spoil out. So that's how we create a 3-bite panel. Panels are either 1 or 3 bites really. Most of the time we try and do 3 bites where we can. It's the most efficient way of doing it. Once you've done that, we need to get the formwork out that we've used to install the water stop in the adjoining panel. So there's actually a piece of metal that we've used to do that. So we lower the grab down and we sort of pull it, just rip it off the side, and that will leave the water bar left in situ without pulling it out, and it will bring that stop end away from the adjoining panel. Once we've got that finished, we then got a nice trench complete, but our support fluid will not be in a suitable condition for us to concrete immediately. So the next, it's difficult to tell, but the next illustration actually shows there's a pump down the bottom of the panel. And what we do is we have a complete refresh of the support fluid that's in there. So we clean it all out, make sure we've got fresh support fluid in there that's going to make sure we get the highest quality of concrete poured in when we do it. So once we've refreshed the support fluid, next we drop the cage in, and we'll show you later on the sort of process of dropping reinforcing cages in, and then we get to concreting. With support fluids, we're always going to tremie the concrete. And tremming is the process of making sure that we're dropping the concrete down to the bottom of a panel and displacing the support fluid. So you can see here we've got 2 tremie pipes that have been installed. So first one on the sort of penultimate frame, and then you can see the 2 of them there. And so those will be used to allow us to pour twice as fast as if we just had one, but also ensure that we don't have any problems with sort of concrete building up in a big mound or something like that. So the number of tremies is key to the volume of concrete, the size of the panel, all of those sorts of factors. You have to almost design in and have planned your number of tremies for your reinforcing cages as well. So you pour the concrete, has to be poured in one go, no cold joints or anything like that. You know, these pours can be hundreds of cube of concrete, so you need to have a good batching plant on side and think about working outside of standard hours as well for it. So we're displacing the support fluid with the concrete, obviously collecting that support fluid to make sure it's processed for reuse if it can be, and then we fill it up. And that's kind of it for forming the retaining wall really. We get the concrete up to the top. There's lots of making sure that we're dipping the concrete as we go, making sure that the concrete's getting to the right levels we expect for the volume we've put in, and lots of QA processes that we'll talk about later on as well. Simple, isn't it? Well, the slightly more sort of really big sister to the grab really is a Hydrophrase. The Hydrophrase is quite a different sort of process, but does end up ultimately creating a very similar thing. But what we're doing here is the support fluid is doing much more than just holding the ground open. We're actually using the support fluid with the Hydrophrase actually to get the solids, the excavated material, into suspension, and we're removing it, we're pumping it out as we're excavating. So what we've got at the bottom of the Hydrophrase is a couple of cutter drums, these rotary cutter drums, and they're mounted sort of side by side, and they rotate in together. All of this is happening under support fluid. So they're digging into the ground, putting that excavated material into suspension within the support fluid. And then just above them, there is what sort of the beating heart of the machine really is the mud pump. That is quite a substantial pump that brings up all of that material, suspended material, and the support fluid all the way up to the top of the mast. And bear in mind, these can be digging 100, 125 meters down to the ground. So all the way up to the top of the mast, back down, round those big reels at the back, and off to the treatment plant. And we're constantly pumping support fluid with Hydrophrases because it is the way that we excavate them. So there's a lot more volume of material, and hence the setup required is quite more substantial. But we process the support fluid, and then we put it back into the excavation, so it's returned in there afterwards. The reason that Hydrophrases are able to get that much higher degree of verticality control compared to grabs is is the instrumentation and the information that we're able to actually get from the tool whilst it's in the ground as well. So the kit itself has inclinometers and gyrometers built onto it. So the operator has that information at his hand. He's watching it. He's got a tolerance that he's got to work within. He can kind of steer it, because the rotary cutter drums can rotate at slightly different speeds, so he can steer it side by side. They're mounted on a table, so it can sort of tilt in the other direction. And they've also got verticality control pads on the section above the rotary cutter drums. So they've got some degree of movement within the excavation that they can adjust as well. So with all of that information, all of that control, we're able to get those much higher degrees of verticality tolerances with this machine. Probably worth noting that we do have some much smaller versions of it, and these are still capable of installing quite impressive verticality tolerances, but whilst working in very low headroom. These are all examples of hydrophrases. We do also have low headroom grabs as well. Not as much call for these machines, but where you can, or where you have to get a diaphragm wall in underneath an operating train station or whatever the need is, and you've got enough space, it's a fantastic solution for it. So yeah, just to sort of show you, I'll go through this relatively quickly. You do have to start the excavation off, sort of second slide along, you have to start the excavation with a grab. I mentioned that the hydrophrase has to be in the support fluid, so you have to start with a bit of a channel, fill it with support fluid, and then the hydrophrase can start working. But same as before, it's going to dig one section down, dig the other section down, and dig the central section down. And we'll come back with the grab to remove the stop end, clean out and refine all of the support fluid, and concrete and reinforce it in pretty much exactly the same way. The only other thing you can do with a hydrophrase is if you are forming a shaft, obviously you've got panels that don't have sort of a right angle perpendicular interface with each other. You can actually cut into other panels, so it's what's known as an overcut joint, so that the hydrophrase itself can dig into the adjoining panels, so that you actually get quite a sort of strong physical connection between them, but you don't end up with a water bar in there. But it works very well for shafts and where you need to get a relatively circular sort of shape installed. If you do single bite panels and you overcut into the adjoining diaphragm wall panels that you've already installed. Okay, so that was me, and now I'm going to hand over to Dave to do a bit more talking for you.
Thanks, Tim. Okay, design and execution. I'm not going to tell anyone how to design a diaphragm wall at this point. I'm just going to run through some sort of key points that you probably need to bear in mind when you're looking at these particular retaining structures. So this is not quite a brain dump, but it's a list of some important elements to think about. Now, a lot of this is about quality control. You have to remember that the whole thing is concrete being poured in the ground, out of sight, from the bottom of an excavation up. So you can't see what you're doing. So you rely on process and quality control methods and competence to get you that end product. The wall is designed to resist the sort of lateral pressures, but quite often these walls are being put in for cut-offs as well. So you need to be thinking about where's the toe of the wall in relation to that, and not just the actual retaining structure. A question that comes up quite often is about the joints between panels. There's no continuity of reinforcement across a joint, and we'll show a joint a bit later on. So this is an unreinforced connection that relies predominantly on shear between the two panels next to each other. I can't tell you what the shear resistance is of a diaphragm wall panel joint. It gets asked on a fairly regular basis, and it's quite difficult to put numbers against. But your wall is designed to act as a single unit based on having a capping beam or wailing beams or whatever else. So you shouldn't be relying on that joint to key the panels together. It's making sure the water's not coming through and the ground's not coming through. It's not part of your structural connection. Another very important one on there is the sequence of the panels and the number of bites. You don't just build one panel and then move immediately onto the panel next to it. You have to wait for the concrete to cure. So you're looking at opening up a sequence of panels along the length of the wall. You don't want to have too many open at one time, because otherwise you start having lots of stop ends in the ground. You've then got to go back and get back out. So it's a balance of efficiency and then also the number of bites. We've talked about 1 bite or 3 bite panels. Going around corners, you have to think about how you're going to construct that panel, what changes in direction. So this is where the experience and input from your specialist is very much required. Tim mentioned the concrete. It has to be placed continuously, otherwise you're going to get a cold joint at best. We had an infamous occasion many years ago when halfway through pouring a panel on a shaft, all of a sudden the concrete wagons stopped turning up, and about an hour and a half later they started up again. And a quick review of what was going on at the time identified that the nationality of the truck drivers corresponded with the football team that was playing a World Cup match at the time, and we ended up with a very large cold joint in the panel. So sometimes external factors come into play that you really wouldn't have thought about. And then support fluid. Talk a bit more about support fluid, but it is a key, because if that's not in the trench, you'll get a collapse. And when a panel collapses, what that actually means is a very large void opens up in the ground, which, if you're in an urban environment next to services, other structures, tube lines, gas mains, is going to rapidly cause a serious problem. So, a bit sensitive. Design solutions. I mean, we can design these in all sorts of different ways. I mean, we use standard retaining wall software, Wallop. If it's more complicated, we use Plaxis. That's the sort of go-to piece of software in the geotechnical industry at the moment. Plaxis 3D is now far more user-friendly and reliable than it was maybe sort of 10 years ago. So three-dimensional modeling is coming in quite a lot. And then structural design, we use either internal spreadsheets or software like AdSec, commercial software. It keeps changing.
Sorry, it's me. I'm trying to stop that for you.
Thank you. But there's other aspects that need to be looked at for these structures. Very fancy software is all well and good, but have you looked at the surrounding environment? And sometimes you're asked to design in aspects you probably haven't even thought about. Thames Tideway, a big issue was designing in third-party future developments. They didn't know what was going to be there or what shape it would take, but we had to take into account a fairly vague 75 kPa over the entire height of the shaft. And when you actually started questioning what was that, what did that mean, it then led to a discussion over exactly what that force was and how we meant to design it in. Another specific problem for circular shaft is the interaction between the external diaphragm wall and the internal lining. It's a problem you don't normally get on a normal retaining wall, where a plain wall for a cut and cover or deep basement, you just got a flat wall, and then quite often in front of it you'll just have a cavity wall, or it might be sprayed lining. But on shafts, you've quite often got an integral secondary lining cast against that diaphragm wall itself. And at that point, you start looking at composite action, which you can use to your advantage, but you do then have to start thinking about load transfer between your in situ shaft and your diaphragm wall built beforehand. So you can get some quite, I'll say, interesting technical problems coming up. But a lot of this requires thought and It's when you come across the things that you haven't had to look at before. What do you have to take into account when you're designing a 100-metre deep shaft? It's very different from something which is only, say, 40 metres. So considerations around the actual site setup, though, and the execution side of it, you have to remember that because we need guide walls, there has to be enough space behind the wall to build that guide wall. So if you've decided when you've looked at your site boundary to put the diaphragm wall on the line, you've got a problem. It has to be set back in to make space for that. And guide walls, although in theory a fairly nominal piece of temporary works, they can turn into quite a significant item if you've got very soft ground and you've got a very heavy rig sat next to it, rather than just being a simple 750 deep lightly reinforced piece of concrete. They can turn into quite a deep L shape with a slab return on the top to carry the rig. So you do need to look into that as a design. You've also got a lot of other bits of kit that need looking at. The stop ends, desanding plants. You're going to have a lot of cage elements. Quite often these diaphragm walls are deep. So if you've got a cage which is 30, 40, 50 meters deep, and you've got 2 of those in a panel, that's a lot of steel you've got to store somewhere. You could work around just-in-time delivery, so it turns up sort of as you need it. But if you've got a big site and 2 or 3 rigs running, you've still got a lot of reinforcement cages to stack up. With all of this, you've also got quite large site crews. So you need welfare for all of those. Working platforms become very, very important with these big rigs. These sort of larger machines like the Hydrophrases, you're looking at 150-ton rigs. They have to work off good platforms. It's not at all unusual for us to actually be working off a concrete slab in order to make sure that it's sufficient to take the loads, and that's a fairly significant item to build into the cost of the project. It's not really practical to have anything else going on site when you're doing a diaphragm wall. There's just so much plant, kit, machinery moving around that it would pretty much have to have everything there and have all the space available. So you really can't be looking at other things going on at the same time. And there's a lot of traffic in and out. Tim alluded to working as with concrete, because yes, if you start pouring 1,200 cube of concrete, you just have to keep going. Some of the tideway sites, we actually had to redesign the walls to have smaller panels so that we can actually cast within the allowable durations on site, because it's okay if you get an extension of time, but if you can't get an extension of time, you're fixed into that period between 8 in the morning and 6 in the evening, and that is the only time you can pour your concrete. And a Hydrophrase is a big piece of kit. This is just one being rigged up. It hasn't collapsed. It is just sat there. It's in the process of being put together. The van on the left-hand side, just behind that, is the cutting head. Just in its travelling frame, that's going to be attached to the body that's lying on the ground. And next to that frame are the black drums, which will be used the actual cutting itself. The reason there's that many there is not that we wear them out. Those will be different thicknesses. That's how you can cut different thickness of wall. And also you can have different heads for different types of materials. So you might actually decide to change them at some point, depending on what material you're going to be going through. But this is just to rig it up before you've even got it in play. As you can see, it's a lot of space. And again, that's off a concrete slab. So the support fluid, we've specifically said support fluid rather than bentonite. Traditionally, bentonite is the material that's used, but that has changed. Its main job is to keep the trench stable and open. It's sat there, it's resisting water pressure, it's forming a skin on the inside of the trench that stabilizes the surface, and it's basically ensuring that there's just enough pressure inside the trench to stop the sides being pushed in. It also is how we can remove cuttings out of the panel if you're looking with a Hydrophrase. And it has a sort of secondary effect around lubricating those grabs and preventing contamination migrating through the wall itself. If you're digging with a grab, we would call that static mud, because once the support fluid is in the trench, the volume just sits in there. Direct mud is where you're using the Hydrophrase, and so you're constantly topping up, because obviously as an equal amount in the top, so you have to start looking at volumes at that point. As I said, bentonite, which is actually a clay mineral, is traditionally what's been used. Polymers are starting to be used a lot more now. Polymer is a bit of a catch-all phrase. There's no such thing as a polymer. They're changing all the time. Different companies use different materials. And we within Soletanche Bachy group internationally have particularly started mixing bentonite and polymer to try and take advantage of the particular properties that each have. This is an area which is constantly being researched and updated. And if you are interested in support fluid, then there is a DFI, which is the American Deep Foundations Institute, and EFFC guide on support fluid. That's the first edition. It's got a lot of background material in there. So it's got a lot in there on the theory about the material properties of support fluids and how they should be used. There's a second edition planned, which will actually build in some R&D of actual sites to update it and make it a sort of a live practical tool. So this material that needs to be stored, if you imagine you've got a panel, it's 500 cube, 800 cube of material, that's in the trench. You obviously need as much, again, sat somewhere to replace it. If you've got more than one panel open at a time, you multiply up again, and you also need to have enough spare so that if for whatever reason you start losing support fluid into the ground because you've hit a cavity or lose some material, you need to have enough to be able to start pumping in an emergency to that panel to stop a collapse. So the photos here are just showing different options around how you might store this. Bottom left is sort of the ideal if you've got lots and lots of space. Big lagoons with either fresh bentonite in it, waste bentonite waiting to be treated, bentonite being hydrated, and spoil heaps. That was part of Lee Tunnel. So you can see we had a lot of space within the sewage treatment works, so we could just spread out and take up lots of space, shallow lagoons. Top left is a sort of more urban environment. It's got a mixture of lagoons and some vertical silos. And then the two photos on the right is where we're using polymer and bentonite. Vertical silos have the benefit of a very small footprint, but you do have to start considering temporary works at this point, because those are obviously quite tall structures. They have to be tied down, nailed down to a concrete slab. And there's a lot of temporary works around desanding plants, because the slabs that they sit on, there's the catchment area that the wet spoil goes into. So you do have to look at where you site these, because you don't want to have to move this. Sometimes it's unavoidable because there's maybe internal foundations as well. But ideally you want to position this once somewhere central, so you're always pumping roughly the same distance and it's not the far end of site. But you have to look at the specifics of your site and what kind of volumes you need. So what does a desanding plant look like? This is what you need if you've got bentonite. You're trying to remove the sand and suspended solids from the bentonite itself, because we try to use it as much as we can. You don't just use it once then throw it away. It depends on the size of the solids that are in the bentonite. You can take out sand and gravel very easily. When you start getting down to clay particles, it's far more difficult because it's almost the same size as the bentonite itself. And you have to start using centrifuges and presses to try and remove that material. So the top left photo, you can see the big orange desanding plant, and then either side of it, those green boxes are centrifuges, and they're like just large scale industrial centrifuges to try and spin out as much of the sort of natural ground that's contaminating the support fluid, so we can send it around and use it again. There are limits set on sand content before you can concrete, and this limits normally also on how much you would allow it to rise up to during digging. So if you're saying you're allowing 5-6% sand during digging, you only say want 2% sand before you concrete, to make sure that you can get the good quality at the end of the job when you're trying to displace that out and trimming it. So what does an actual stop end look like? Well, on the left, you can see the frame with the rubber strip embedded in it that sat at the end of the panel. You've got the cage sat in front of us. So behind that CWS joint former itself, it's just the ground. In front of it is the trench. It's been dug to depth. The steel reinforcement's been placed. You can see the beam that's hanging that off the guide walls. The right-hand photo is showing after a CWS joint has then been removed. So the panel has been concreted. The next panel has now been dug out. The CWS joint has been removed, and you can see the shape, the concrete form is left there, and the CWS joint, the actual water stop, is cast into the concrete itself. So the action of pulling the former away does not damage that water stop. It's a very robust, heavy-duty rubber strip. So that's now the end of the panel. So you can imagine when that's concreted, you then get a concrete-to-concrete connection up and around that, and you get a nice watertight joint with a water bar running down the middle of it. Cage deliveries, you're going to be restricted on what you can actually get into your site. So typically you're looking at cages which are maybe 2.5 meters wide and maybe up to 15 meters, 17 meters long. You can maybe get some special deliveries in longer than that, but this is then down to detailing. So you have to think about this as part of your design. It's all very well saying I need a 50-meter deep wall, but you have to work out how you're going to build it. So part of that is working out what does the actual steel look like, and it's got to be lifted and put into the ground. So you can see in the bottom picture a site lifting frame, because obviously in the factory where these are made, they've got overhead gantry cranes that are quite happily pick these cages up and drop them on the wagons. On site, you don't have that, so you have to think of other ways to pick them up and move them. They may not have a centre of gravity where you think it is, so you have to also look at that when you're thinking about lifting operations. The polystyrene on that lower photo is where we're going to do an overcut joint. So part of that overcut has been filled with the polystyrene, so the machine only has to cut out the edge of it rather than taking out the entire large chunk of concrete. It just reduces the wear on the Hydrophrase drums. We mentioned glass fibre and also ground anchors before. The first one on the left has got two details in there. The large angled tube is a reservation tube for an anchor. So on the top of the cage, as you look at it, is the front face. So there's a box out on the front to make it easier to find that reservation tube. This is the top of the wall, because you can see the debonding foam on the bars to the right of that cage. And then just below that reservation tube, you've got a line of spacers to keep it centralised in the ground. And then there's another box out, and that's actually a slab connection, and you can see the anchorage bars from the couplers bending down into the cage. So you've got a temporary anchor connection there, and then the permanent slab connection as well. The two right-hand photos are showing fiberglass. The top photo is all fiberglass, and the lower one is a mixture of fiberglass and steel, which is just a function of where the tunnel eye hit the cage. The top photo, you can see just about that there's a steel frame around the cage, because if you try and pick up a cage made entirely of glass fibre, it's almost definitely going to break its back and shatter. So you have to think about the temporary lifting to get that from horizontal to vertical in order to put it in the ground. Because they're delivered horizontally, you have to get them vertically. Now that's actually a nice simple cage. You can see plenty of sky through it. It's not too heavy. There's not any really complicated steel on it. There's a couple of box outs, so it's slightly weighted on one side. But all in all, that's not too bad. But there's lifting still required here in terms of where you pick the cage up and the temporary steel you put into it to stop it racking or trying to flatten when you pick it up. So there's quite a lot of temporary works detailing goes into diaphragm wall cages as part of that process. It's not required as part of the actual design, but it's a key part of getting them into the ground and built. Just a couple of more recent updates on what we're doing with cages, because in the past, cages were just lapped, connected by U-bolts. That's changed. It's a combination primarily of safety. If you've got 32 mil, 40 mil bars, and you've got guys with their hands around them, people get hurt. So as an industry, there's been an increasing push to try and move away from that, try and protect the workforce. And a secondary consideration is with the change over to Eurocode, slaps got even longer than they were before, and it just became impractical to try and lap over 2.5 metre height. So what you're looking at there is super latch. It's a commercial system. It's not one of ours, but it allows you, the latch is fixed on the top part of the cage, and then as it's lowered down, the red portion slides over that blue. They don't have to be painted like that in the real world, obviously. It just slides over and clicks shut, and the two sections of cage are connected. We've used them successfully on piles and diaphragm walls, and it's a very robust system. You just have to make sure you've designed in enough of them to carry the weight of the cage. The right-hand side is a completely different issue, but again, a very important one. It's to do with breaking diaphragm walls to cut-off level. Historically, this has all been done with peckers, hammering around the cage, trying to break off debonding foam. Noisy, messy, lots of dust and vibration. We came up with a system at Tideway where we built in couplers with plastic caps, which allowed the diaphragm wall to then just be horizontally cut with a wire saw at the required level. And that's what you can see on the bottom photo. The bars there have been screwed in afterwards. So for the follow-on contractor, a nice, neat solution. They just come in, take it off in one lump, and then screw in the bars. And they've got your connection into the capping beam. So much, much simpler than the old method of breaking out around the cage, which always ends up damaging things at the same time. Concreting, we'll mention it again because it is the critical part of the process. You can see top right photo there. It can be quite congested. There's serious safety concerns to look at here. If you're trying to get 3 concrete wagons up, because they have to be pouring concrete at the same time to maintain that horizontal level within the panel. If you've only got one tremie, the concrete will not flow evenly across a panel. There's limits on how far you should be allowing the concrete to flow. If it's flowing more than about 1.5 meters, you've probably got a problem with inclusions in the future. So you have to look at how many tremies you've got and keep the concrete at a constant rate into all the tremies, which requires good control of what's happening with the wagons, but also dipping the trench as well to make sure that you know where the concrete is. And obviously it's got to be done in one hit during the shift. So on to quality and testing. So the concreting, we would always end up doing work up front to make sure we've got the right mix. And that's a lot of additional tests will be done beyond what you'll just be doing on site. You'll be looking obviously at sort of slump and flow, and slump flow is now the preferred test rather than a slump or a flow test. You also need to look at bleed and segregation, because you're looking at how the concrete behaves when it's poured in the trench and how it flows around the cage to make sure you get good consistent concrete, because this is concrete that has to self-compact, and you've got no way of vibrating this into situ, so it has to do that flow and self-compaction without letting the aggregate start settling out. There's a lot of additional tests that are now recommended for deep foundation concrete, and again there's an EFFC DFO guide on this, which is very good. That's in its second edition. It's taken the R&D element on board from sites, and so again that's worth a read if you want to know about concrete specifically for deep foundations. That covers piling as well as diaphragm walls. The bottom right photo is showing an alternative that we use occasionally, rather than sort of the traditional top photo, which is concrete wagons pouring down a tremie into the panel. That lower picture is actually a flexible tremie on a tracked vehicle. So it allows us to reel out and reel in the tremie without the use of cranes and swinging tremies around. So just another little innovation that we've come up with. So we talked about the verticality, but how do we know what the verticality is? And how can we check it? Sorry about this, it's playing up again.
It's not me this time, I promise you.
The codon is actually a sonic method of checking the trench. It's lowered down the excavated panel after it's been completed, and it takes effectively a sonar profile of the inside of the panel. And so from that, you can tell what the actual shape of it is, and does it deviate? Are there any bulges, any additional overbreak that you should be worried about? And you can obviously do this when you've got panels cast either side, so you can check that you've got the panels where you think you have. Now, the advantage of this normally is you just get a simple 2D plot that shows the reading. We've taken that one stage further and worked out how to put that into 3D software, and it allows us to then plot the as-built alignment of the wall in relation to the original model. So rather than just the client or the engineer having these sort of slightly confusing paper traces to look at where they're not quite sure what it is they should be deciding is it right or not, you can now get an actual three-dimensional model to compare. And on the right-hand side, the reason it just looks like a continuous tube is because actually it was very good. But the different colours show you whether it was being, and you can just see around the very bottom of that shaft, some of the panels are slightly drifted out of position. But it's just, again, just another little useful tool that allows us to show exactly what's being built at the end in a slightly more user-friendly format than the traditional bits of paper. So I think that's the last bit apart from the nice testimonial from guys at Tideway, which you'll have to click across to, Tim.
Yeah. Sorry about the technical issues with the clicking. Ronan, that's us. Sorry we overran a bit. Maybe he's gone already.
No worries at all. No worries at all. I was talking to myself, as is traditional on Zoom. Thanks very much, gents. Very, very interesting. I think, as you can see from the attendance, we've over 200 on tonight. Lot of interest in the topic. So look, what I might do is I would just fire into the questions. We've quite a few. You can click on the Q&A button as well, lads, if you want to be having a look at them. I'll just go through them in order. The first one, I suppose, is maybe somewhat unusual. It asks you, Tim, why did you want to do engineering? I might point out that our CAO system for applying for college places, there's a deadline coming up. So perhaps Robert, who asked the question, has a son or daughter, perhaps considering the profession, but if you wouldn't mind.
No, not at all. No problem at all. I think during at school, I always had a bit of an affinity towards maths and physics. They just seemed to come a bit more naturally to me than other subjects did. And my father and my grandfather were both worked in mining, actually, engineering. So there's been a bit of a sort of history of engineering in my family. Interesting, the choice of what type of engineering to do was almost an accident. I think when I came to apply for university, I applied for 5 mechanical engineering degrees and 1 civil engineering degree. And I was very glad that I ended up on the one I did, actually, because I've never looked back since. So yeah, it was. I think engineering's always been sort of found quite natural for me, and yeah, I was very fortunate to get sponsored through uni as well. So that sort of helped along the process for me. So yeah,
absolutely. Next question. What's the difference between a peanut-shaped shaft and a scallop-shaped shaft? There's someone.
That sounds like semantics to me. I mean, a peanut is because it is sort of there can be a figure of 8. There can be slightly different shapes. I mean, a scallop would imply probably more than 2 intersecting circles, but it's just I mean, at that point you start talking about cellular if you have more than 2 normally. It was just the peanut was what people called it because it was a sort of a neat name to give it, but it's the same sort of structure.
Fair enough. Next question, which I think maybe you might have answered after the question was asked, but what's the fluid used to keep the excavation open? So you were saying kind of bentonite, but it's not necessarily.
Yeah, it as Dave alluded to, it is a field that's constantly evolving. Bentonite is quite common, and bentonite's a naturally occurring material. It's a clay, and then polymers more and more common now. And quite regularly, we're mixing them together as well to get the best of both worlds, really. So yeah, it's a substance within water to create a liquid with the properties that we need it to have, and they do vary for different ground conditions, different types of machinery, and all equipment that we're using. So they're designed specifically to the project, the ground conditions, the equipment, and all that, really.
So next one there, just do the grab and hydraulic cranes have software to determine how deep the excavation is, or is it determined by the number of digs taken, or kind of mechanically, I suppose? Is it a combination of both?
They'll have readouts in the rig that it knows how far it's gone down. You know, the driver presses a button to tell the machine that it's sat at ground level, and then it knows how much cable has been reeled out. The same as with drilling with piling rigs. The instrumentation is all automated now.
No.
You'd also normally dip a diaphragm wall panel, possibly not if it's 120 meters deep, because that's going to be a really long tape. Take a really long time to wind it in at the end. But yeah, you'd normally quite often dip if it's a sort of standard one. Same again, it's the same as you do with diaphragm, say deep rotary bore piles.
Yeah,
it's a sort of a quality check just to dip it as well.
Yeah. Would lads on site have kind of marks on the cables and that, just kind of rough benchmarks? You wouldn't be taking any design off it or anything, but
not normally, no, because something on the cables is going to get worn off, or it's going to get caught up. So it's done with the machine, and so you can always check by the dip afterwards.
Okay. I'm not sure I understand the question myself, but has Bachy used these machines for the excavation of landfill or just for structures? Is that for the construction of a landfill? I'm not sure the intention.
I mean, we have used them to create cut-off barriers, so to prevent leachate, those sorts of things escaping from landfill, if that's what you mean.
I think that's probably the intent, yeah.
Yeah, I mean, if you mean actually trying to dig out landfill, I'm not sure that would be particularly fun.
Yeah.
Conceptually, I don't see why you couldn't do it, but
yeah. I think probably you're right there. Again, I think you probably answered this one. Does groundwater impact installation? Obviously.
Yeah. I mean, generally, we need to maintain the level of the support fluid about 2 meters above groundwater level, so that we've got that hydrostatic pressure pushing against the sides. Obviously, we can't allow groundwater level to get too high, or else we lose one of the things that the support fluid is doing. So there have been occasions where we've actually had to increase platform levels so that we've got that pressure head to allow us to maintain stability of the bore. I think, I don't know whether you want to add to that, Dave, about flowing groundwater or anything like that, problems you might come across.
I was going to say, if you've got a very mobile groundwater, you might have to think about if you have a risk there. And the other one, of course, is salinity. If you're near the coast or near marshland or something like that, something which is a bit brackish, that can change the properties of the bentonite, which can then give you problems with how it behaves. So the short version, groundwater, yes, it does affect it. It's one of the things we'd look at for a project.
What are the advantages of a D wall versus a steel combi wall?
They're two different solutions.
Okay.
Really, I mean, a combi wall would be quite often used for something like something which is actually offshore. You're driving in a dock or you're building a quay or something like that. You could build a combi wall in water. But they're essentially two very different solutions. A steel combi wall, you've got a lot of steel in the ground, you've got potential issues over durability and corrosion on the wall. It's going to be more flexible and have less structural capacity, potentially, compared to a D wall. Might take a bigger footprint. A D wall, you might have a slimmer structure, but they're two very different solutions. It's like saying a D wall versus a secant wall. It's like there'll be a reason why you've gone for one over the other. And normally in a project, we would certainly weigh up all the different options. Is it a D wall? Is it a secant wall? Is it a combi wall?
Sorry, Dave. So it's similar to saying, when would you choose a CFA pile or when would you choose a driven steel pile? It's to suit the ground conditions, the situation you're in. Yeah. We do use diaphragm walls to create key walls. We showed London Gateway there, where we were creating the face of the key there using diaphragm walling techniques. So there are situations where they sort of are quite used in similar situations, but they've each got different merits, as Dave says.
Fair enough. Next question, Liam Edwards. What's the percentage of bentonite versus other fluid / polymer? Depends, I presume.
That's I wouldn't know, to be honest. I mean, because I think it's probably changing. It's probably, I'd say, if I said 80-20 bentonite to polymer, but it also depends whether you're looking at a Hydrophrase job or a grab job, because if it's a Hydrophrase job, you're probably going to go with a bentonite or a bentonite polymer mix. If it's a grab, you could use either. And one of the issues around the Hydrophrase is because you're pumping the liquid, you have to use different polymers compared to a grab. You have to use short chain polymers, not long chain polymers, because the actual process of the whole thing being pumped and churned around can break down the polymer. So it's probably still more bentonite than polymer, but that's changing on a sort of yearly basis, really. And again, it's something we assign based on the project.
Good. Liam Edwards is wondering, what's the deepest wall that's been achieved by yourselves? Is there a limit ultimately?
I think Lee Tunnel is probably the deepest panels we've dug, haven't they?
In the UK, yeah, because they were about 100 meters. In the group, we've gone to about 125 meters. I mean, realistically, there's not a a limit. You can just keep adding. You just need to set out with a more, the right amount of cable or whatever on your winch. The only thing you do have to start bearing in mind is when you're getting down to sort of 100 meters depth, the pressures in the groundwater are extreme. So you actually get issues if you're not careful with the pressures externally in the groundwater can be higher than the pressures in your hydraulic system itself. Strange quirks start coming out, but to go more than 100 meters, you need a really special reason.
Yeah,
it's a long way down.
Long way down, yeah. Can saw cutting of the diaphragm wall for capping beam be utilised in seismic areas?
I guess the only potential issue on that would be around the use of the coupler to connect the bar in. But I think at that point, because you've already had to address how you've connected your cage up, and I can't see why it wouldn't. Off the top of my head, I mean, the UK's not particularly seismic, so it's not a problem we've had to come up with particularly, but I can't see why it wouldn't be possible.
Yeah, okay. With the rebar not being continuous between the panel, how much effect does the hoop ring stresses have on the stability of the shafts?
Well, hoop stress is how those shafts stand up, basically. They are designed as self-supporting, so in its simplest form, a circular shaft doesn't need reinforcement, because the concrete stress is dealing with all the forces in it. You need reinforcement in there because you have to look at buckling and things like that, but the hoop stress is what's making that shaft stand up.
Okay. How is verticality corrected if outside tolerance in the direction of an internal basement?
I mean, we'd obviously not get outside of tolerance, I think, is the answer to that question. Yeah, Dave, what do you think?
Well, the Hydrophrase is the simplest because it's easiest to spot it going out of alignment, and you can actually actively steer it. With the grabs, it's a bit more difficult. One of the key issues with the grab is you have to keep rotating the grab around to 180 degrees as you dig, because what you'll tend to find is that they will tend to drift slightly. So by rotating it on a regular basis, you'll keep it fairly central. But really, you just have to make sure that you're keeping an eye on where it is. And worst case, you might have to put a chisel down and try and shave off one side of the panel to bring it back in. The hydraulic grabs, we can do a little bit of steering with them in the ground, but the main thing is it's staying within tolerance. As Tim said, it sounds a bit sort of facetious, but actually that's the best solution, is to just dig it properly in the first place.
Fair point. Can you explain how the bentonite is recovered when you're pouring the concrete?
Yeah, I mean, it's obviously displaced out, so it comes out the top of the panel, and we just set up a sort of bund around the outside of it and catch it and pump it back into the
It's just pumped off. It's just pumped off as it's displaced up. So again, you're just sort of taking it away, matching the volume of concrete that's coming up.
Okay, perfect. What happens to the guide wall? Does one side become permanent and the other side is excavated?
The bit guide wall on the inside, yes, that gets taken out with your bulk dig. The bit on the back face, it depends on the connection at the top of the wall, but quite often it will come out when the capping beam is being built, because it's normally going to be in the way, so the whole thing just gets ripped out. Okay. And we have looked at some of the major things like HS2 and Tide, where we actually design them in lengths with lifting points in them, so they're easier to remove at the end of the job. So it's not about just getting in a pecker and breaking it all up. You can come in and fix onto the lifting highs and take it out a lot simpler, just to get to speed up that process.
Okay. Skip down a little bit. How do you create the initial excavation to install the guide walls and working platforms?
Pretty conventional techniques for guide walls, I think. Just excavators digging out sections and formwork, to create them. They need to be pretty good quality. Quite often the guide walls are reinforced, so we're just creating a reinforced concrete ground beam in quite a conventional manner, really. I think there's too much more than that, really. Platforms are designed bespoke to the ground conditions and the loading that we're going to be imposing on them. There's ways of using geogrids to get them a bit thinner, or as Dave says, we just end up with a concrete slab quite often. So yeah, it's just to suit the conditions, really, but nothing particularly clever in that, I'm afraid.
Query from Ronan Daly. Do they work well in low or zero SPT alluvial silts or clays? I think you said that it's hard for the bentonite, it's hard to reclaim it, but is there other issues?
If the ground is that soft, trench stability starts becoming a serious problem. But if you're actually building any kind of pile or foundation element in ground that soft is a nightmare, because even if you can keep it stable, the other problem then actually is also not having the concrete just slump into the ground. So it's not unknown. I mean, Belfast sleet just is not exactly an unknown material to some of you guys, I'm sure. And it's sometimes you have to pre-treat the ground before you can actually build the diaphragm wall, the pile, or whatever. So it can be done, but in material that soft, you could well end up having to do pre-treatment.
Next question. If a circular shaped wall is required, is fiberglass the preferred option over steel reinforcement?
No, the panels that we create will always be rectangular panels. So whilst the walls look circular in shape, they're actually made up of straight sections.
Yeah.
So the bars themselves, the cages, are always going to be rectangular. We don't have a way of actually creating a true curve or anything in there.
And yeah, we only use fiberglass if there's going to be a requirement for something like a TBM to go through the wall, because they don't like chewing through steel. Otherwise, it's steel because it's cheaper than. But yeah, the glass fibre is normally where you need to make a hole in the wall afterwards, and it's just easier to cut. It's got the same tensile strength in terms of bending, but it's much easier to drill out than high steel.
Okay. The question there, I suppose when you have poured a panel, you were saying that you move on from it. How long before you can come back and work next to that panel again, or I suppose the concrete strength?
Yes, you normally leave it sort of 2-3 days, but which is not normally a problem, because to try and build a panel in a day, they have to be quite small panels. It's sometimes, for the job we're doing up at Old Oak Common, where the panels are only maybe 20 metres deep, we can dig and concrete and build a panel in a day, but normally it's going to be a process of 2 or 3 days to actually build another panel. So by the time you've started with your first panel, gone and built another panel and finished that, it's going to be at least 2 days before you get back to that first one anyway. So it's enough time for the concrete to get an initial cure on it.
Are there any particular precautions for the panel that closes the shaft? I suppose the final wedge.
That's a leading question. That is someone. Yes, you have to make sure you've got your water pressures balanced, because otherwise you run the risk of having a water table inside and outside your shaft which aren't the same, and then you can get a panel collapse. And so you quite often have a dewatering well put inside the shaft to allow you to balance that pressure and not get caught out with that. So yes, to the person who asked that question, that probably knew that answer anyway.
We have had it, so that's why.
Oh yeah, it's a fairly well-known phenomenon.
Yeah. You had mentioned cold joints, and somebody asked how you do address them if they do occur.
It would depend on what it actually looked like when the wall was excavated, and what depth it's at. Because your main problem is going to be keeping the water out. Probably if it's a purely cold joint and it is just a sort of effectively a crack, the potentially water could come through. You would probably find that you would excavate down to just above it, And then you possibly look at drilling down through the wall with some resin sealant, something to try and seal it up. If it was shallow, you might just do that from the surface. But essentially, you're going to have to try and seal that crack to make sure water doesn't come through, as long as it's stable.
It's maybe somewhat how long is a piece of string, but question, what would be the typical mobilization period from contract award to getting on site, including, kind of design and that? I suppose it very much depends on the project.
Yeah, absolutely. And also the kit itself, the grabs are pretty common. They're just mounted on cranes. There are lots of cranes around. The hydro mills, the hydrophrases, there are a limited number of those in the world. So they do get booked up. So we tend to be trying to book them possibly years in advance if we know about the project. So, if we're looking at hydrophrase projects, we need to be thinking about the kit, where it is. At the moment, a lot of them are going to be tied up on HS2 for a little while. So it's then, where is the stuff after HS2 for those to go to? Beyond that, I don't know whether, Dave, you want to say how long it takes setting sites up and things like that. More experience.
No, I mean, it's about the lead in time. Yeah, the hydrophrases, there's a sort of a European pool, a Middle Eastern pool, and a Far Eastern pool. So it has been known for a hydrophrase that's been sat in the Far East to be stuck on a boat and sent to the other side of the world, because if we need to get them, we move them around. But it's like any job. It's the lead in time giving us the advance warning. So you need months to get all those ducks lined up. It's like any major construction project. There's a lot to be done, and then depending what it is, you might find you need a couple of months just to get the design sorted out anyway. So it ties in with that as well.
I'm just looking through the questions. I think quite a few kind of overlapping questions. So I might just ask one last one. And just hydrophrase, are there any actually, I suppose, permanently located in Ireland? I suppose the query there was the Metrolink project, which I don't know if you're familiar with the proposal, but that if something of that scale came online in Ireland, I presume we're going to either yourselves or the continent looking for machines of that size.
Yeah, I mean, we're aware of the Metrolink project. The way they're talking about the moment of sequencing stations would need more than one machine, definitely. You get one or two machines per station if you really want to create them at a very similar time, although there's ways of looking at smoothing it out. There are none permanently based in Ireland, or none permanently based in the UK either. We don't actually have any. And I think that's true for all of our competitors as well. I don't think there are any at all based in the UK or Ireland for any of the other people that do these techniques. It's not just us. Yeah.
But it's not common to get hold of them. They just get shipped in. Some of the ones we were using on Tideway came in from Spain.
They're big expensive machines. You can't have them sitting idle, so they follow the work. Which obviously makes sense. So look, gents, as I say, there's a few more questions, but I think you've probably covered them already in the other questions. So I guess I might draw the evening to a close. I suppose one of the great things about the virtual environment is that we've been able to reach out to quite a large audience tonight. One of the disadvantages is that there's nobody to give you a round of applause, which I think you very much deserve. As I said, there was great interest in the topic, obviously because of the amount of people, but also the number of questions, both in the Q&A and in the chat line, is an indication of of people's interests in the event. So on behalf of myself, the other attendees, and Engineers Ireland, and I thank you very much for coming and speaking to us tonight. I'd also like to thank Ian McCarthy of McDonald Piling, who kind of organised the event for us and kind of put us in touch with yourselves. So very, very grateful.